going to scoot this over here and move it around a little bit. Huh?
Never mind.
Yeah. I did have that other one moved over. You're good, though. It's not a big deal. So, this is the beginning of geology class. Welcome, everyone. We're going to start off with the nature of the solar system. We do start small and work our way big. The solar system doesn't sound small, but truly it is. And especially when you get out into the universe, the solar system is our own little tiny neighborhood of the universe. And so we're going to start here with some ancient science and kind of how we understood the solar system. It begins with the ancient Greeks. They didn't have a lot to work with. There were no telescopes really at that point in time. There were no computers. They had basic mathematics, some slightly advanced mathematics, but nowhere near what we have today. And really, they just kind of had to think about things. They had philosophical arguments and thought experiments. And one of the thought experiments I like to start with is the bow and arrow thought experiment. And the idea is early on, when we still kind of considered the Earth the center of the universe, and we didn't really even understand the stars, we kind of thought of it as a black curtain with holes poked in it that kind of let the light through. And they even kind of refer to this as the celestial sphere. We didn't really understand how big things were. And so one of the thought experiments that set us on that path was, what if I could build a large bow and arrow, like a really large bow and arrow, or maybe just a small one that works really, really well? And what if I could shoot an arrow to the moon? Could it stick in the moon? Could I do that? And they thought about it and they talked about it and they were like, yeah, you could shoot an arrow to the moon, definitely. And so the next question was, well, if I can shoot an arrow to the moon, obviously we don't have anything to take me there today. Could I go to the moon and pick that arrow up? And they're like, yeah, we could build like a catapult to throw you there, or like an airship or something crazy that doesn't exist, but we could do it. It's philosophical. It's not in reality. It's just what if. And so he said, so if I go to the moon and I pick up my arrow, what would happen if I shoot it the other direction? Like not back at Earth, but away from Earth. What would happen then? And they thought about it for a long time, and they eventually came up with it would just keep going until it hit something. And that something wouldn't be like the black curtain. It would just keep going until it hit a star or another moon, or they didn't really understand these things yet, but they agreed that it would just keep going. And so they just kept replaying that scenario. If my arrow keeps going until it hits something, could I personally go there and pick the arrow up and then shoot it again even further? And the answer was always yes. And so that idea, which isn't even really like a concrete scientific idea, it's just a thought experiment, opened up how we thought of the universe and space in a way. It wasn't really scientific. It wasn't written down or attributed to one person. It's not particularly part of history. But this is how we do things sometimes, especially early on, when we don't have equipment to make real science happen. One of the things the Greeks did do very well and scientifically was they looked. They looked at the sky, they looked at things around them, and they wrote things down. They had language, they had writings, they had math. They took very good observational data. They weren't always the best at explaining it, but they took it very well. And so what we start off with is the geocentric version of the universe. Geo meaning Earth, and centric obviously meaning centered. So the Earth is in the center of the solar system. This we had for a very, very long time. We had some interesting things to try to explain it, which we know now didn't work out and aren't scientifically valid. But as I'll show you in a little bit, at the time, they checked all the boxes. They did all the things they were supposed to do. And it wasn't really their fault they had it wrong. They didn't have the tools to actually get it right at the time. It would take a very long time for them to do that. So here is one of the models of early understanding of the solar system. You have the Earth in the middle, and you have this very complicated contraption to explain the movement of the stars and the planets, which we didn't even really know were planets yet, outside of us on this celestial sphere, which is only slightly upgraded from the curtain with holes poked in it. Also, you have a picture of I think this is called the God's Eye Nebula. I'm going to make a couple points. First off, if you ever make a PowerPoint for any reason, whether it's class or anything, if you just throw a picture up here without any context, your professor is going to get mad at you. I'm going to be mad all through all these PowerPoints. Like, give me something. Tell me what is this called? Where did you get this picture from? What context is? You don't have to have a paragraph. At least give me something I can go and look up and have some more information about it. And also, this picture doesn't even make sense. You're talking about ancient astronomy. This was not discovered until we got satellites up into space. You could not see this from the Earth with any telescope. This doesn't really make sense in the context of where we're at and what we're talking about. Okay, so the first thing is we do notice some things are weird in the sky. As we look out and they're tracking the stars, which they do very well, they go out every single night, they write down with math and angles and precise coordinates where the different stars are in the sky. They notice 7 wanderers. These are the planets, well, including the sun, but these are planets and moons that they don't really have a full explanation for, and so they didn't even call them planets. We didn't understand planets yet. They were wanderers. And the reason they're wanderers is as you look out into the sky, most of the stars don't ever move. Like, they move around us, but they don't move relative to each other. If you look up at the Big Dipper, it's always going to look like the Big Dipper. Those stars are always going to be in the same formation until you're 99 and you go out on your last day and look up there. It will always look exactly like the Big Dipper. Now, the other stuff, the wanderers, they move around. They don't stay in one spot in the sky. They're constantly moving. Some of them even move in a weird way, like Mercury, Venus, Mars. They have a pattern that we call retrograde. And so I have it up here on the board. And retrograde is essentially describing how, as you look from Earth, some planets are moving across the sky like all the rest of the stars, and then in certain times of the year, they literally make like a little loop and head backwards for a little while, and then they come back forward. If you know anybody that is into astrology, which is not a science, it's more, I don't know, it's almost like a non-organized religious belief, I guess.
Pseudoscience.
Yeah, you could call it pseudoscience, but it's, yeah, I don't know. I don't want to like trash on astrology or anything. That's not the point of this. But no, it's, whatever makes people happy. It could be called a pseudoscience. It could be called like a non-structured belief system. Maybe not even a religious belief, but a belief system. But they very much talk about Mercury being in retrograde, Mars being in retrograde, and how if you're like an Aries or a Pisces, it'll mess up your day or mess up your week. And that's what they're talking about in retrograde here. The planets are literally moving backwards in the sky compared to how they're supposed to go. And this was really the first problem that we had that we couldn't solve accurately as far as observing space. And so if you come back over here, they talk about the sun, and the sun was one of the wanderers. If you look at the sun, it's always moving around the sky. It's not next to the same set of stars all the time. The moon, obviously, is a wanderer. It's the closest one to us. It's the one we probably knew the most about. And then Mercury through Saturn. So we knew about Mercury, Venus, Mars, Jupiter, and Saturn. Jupiter and Saturn are really far out there. They're also extremely large, and so we could see the light reflected off of them. At this point, though, I don't think that they knew they were planets. They were just points of light in the sky. They probably thought they were the exact same thing as stars. So, here we go. This is called the Ptolemaic system, named after the, I think it's Greek philosopher Ptolemy, or if you want to pronounce the P, Ptolemy. I'm honestly not sure exactly how it's pronounced. I need to look that up. But you have Earth in the center, all the other planets, including the sun, orbiting around us. Note that they have all the orbits in the same direction. This is actually correct. Everything in our solar system orbits in the same direction around the sun. That is kind of a relic of gravity and the early part of the solar system. They've got a couple things right. They have the moon being closest to the Earth, which makes sense. They have Mercury and Venus, which aren't, I mean, if you switch the sun and the Earth, those are kind of correct because Mercury is closest to the sun. Venus is the next closest planet. This is kind of wrong, though, because Venus is closer to us than Mercury is. And so that's one of the things that I kind of see stand out that maybe they should have had right. Then you have the sun, which really the Earth and the sun have switched spaces, which is maybe something that they could have caught on to, but they didn't. Then you have Mars, you have Saturn, Jupiter, and then that's it. We couldn't see anything beyond that without a telescope. One of the things I will point out to explain the retrograde motion, and they've got another image for this, they made the planets orbit around a single point in space, which, as we know today, does not make sense and is physically impossible, but they didn't know that. Who discovered gravity? It was Newton, and Newton wasn't like ancient Greek. He was relatively modern, and so all of this is being done just by observation. They didn't have an understanding of gravity or a gravitational pull. This is really being done on the fly. So they introduced Ptolemy and the Ptolemaic system. This is AD 141, very, very early on, 2,000 years ago. And he had the geocentric model. He tried to explain retrograde motion, and they'll show you that well, actually, we can go ahead and go to it. Here's how we see retrograde motion. Obviously, this is a correct pattern, but you have the sun in the center. The Earth is orbiting around it. Mars is the next planet out. So these lines show you kind of where we see Mars from Earth if you're looking at the night sky. And as Mars comes up and kind of passes us, you can see it go this direction in the sky. But because we're closer to the sun, at some point in time, we're going to kind of speed up relative to it. We're going to change direction. And so as we kind of come through here, this section, you can see these lines cross over. And Mars appears to go backwards in the sky. I think this is like you're talking days to weeks, not a real long time, a very quick portion of time. Mars goes backwards in the sky, and then as we kind of turn that corner and we're both heading away from the sun, it kind of goes back to the normal pattern. And so this is that retrograde motion. Sometimes it looks like a little circle depending on the angle. Sometimes it just kind of stops and goes back and then goes forward. They couldn't explain it. They didn't have a good explanation. So in the Earth-centered model, they put the planets around a single point, which is wrong, but pretty impressive. Like, it's very advanced. They use complicated math to figure out a way to show these planets making these motions as we observe them. And so this is the Earth in the center, and with that cycle, the epicycle, this is your little retrograde motion part. This is how we're going on. Now, how does the Ptolemaic model of the solar system follow the scientific method? These first 3 bullet points. It's based on observations, precise observations. It involves a hypothesis. It was maybe wrong, but they did guess it how it would work. And was it testable? Yes, they created a model that explained the motions, and that model fit the observations. They did have a couple problems that they couldn't figure out precisely, but they didn't know about gravity yet. They didn't have advanced instrumentation or advanced math. They just kind of did what they could do. So how does it fail the scientific method? At the time, it didn't, but as we progressed, we got more information, more accurate measurements, and we also understood that you can't just orbit a single point in space. And so we kind of figured out that that was wrong. Now, it didn't take us a short period of time to figure that out. It took a long time. Copernicus comes along literally almost 1,500 years later, just a little bit below 1,500 years later. So well over 1,000 years, we kept this Earth-centered model until Copernicus came along, and he concluded that the Earth was a planet, along with the other planets, and that we orbited the sun, and the sun was in the system, in the center of the solar system. This was not a great thing for him. Obviously, today he's celebrated. We call it the Copernican theory, or the Copernican model of the solar system. At the time, he was heavily vilified for this. Humans do not necessarily like change all that much. And to be fair, if you look back in history, that's a good thing for us. The reason we're here today is because we resist change. You eat the same thing every single day, you survive. Your buddy brings a new mushroom and he's like, hey, look at this. Doesn't it look delicious? Eat this. And then you die. So we kind of got used to, no. This is how things are. Let's keep it this way. This is the safe way. But he brought in the sun-centered model of the solar system. It explained a lot of things. And the more people looked at it, especially the scientists that studied space and the way the planets move through the skies, they were like, yeah, this is probably right. One of the things that really helped was the phases of the moon. In a Earth-centered solar system, the phases of the moon, the full moon, the new moon, the waning and waxing moon, don't really make sense. Once you put the sun in the center and the Earth way out here, and we know from visual observation, the moon is the closest thing to the Earth, and it goes around us once a day. Once you figure that out, now the phases of the moon make a lot of sense. And so it took a little while. We didn't accept it immediately, but this was the beginning of us really understanding our place in the solar system and how things worked out. And so they do have the two different examples here. And look, nice little paragraph at the bottom. That's all I'm asking for, just a little bit. So we go just a little bit ahead. Their lifetimes almost overlap, Tycho Brahe and Copernicus. Tycho Brahe comes in, and this guy was just a lab nerd. He made lots of precise observations, and he tried to find the stellar parallax. Any sports fans recognize this term? This is a term that we talk about in sports at least once a year, in football and in hockey. And basically the idea is, depending on where your camera is situated, it may look like that football crossed the plane. You may see it and think, oh, that's a touchdown. But when you get to a different angle, it's clear that it didn't. That is the parallax, and it causes problems based on where you're viewing things. And so what Tycho Brahe understood because of Copernicus was that, let me come over here and draw this. So y'all warn me before the bell rings. 3 minutes, that's not too bad. So actually, let me go grab a marker real quick. So what Copernicus got us to the point of was that the Earth is moving. It's not in the center. The sun is in the center, and the Earth is over here, and it's kind of moving around. But because it's over here and it's moving, it can also be over here. And the Earth, while we think it's really big, as far as looking at things in space, it's a tiny little point in space. But if we can take measurements from one side of the sun while we're here, and take the same measurement looking at the same star from over here, you can really get a little bit of distance, and you can triangulate the things that you're seeing. And that is the parallax that Tycho Brahe was looking at. You have to take a lot of measurements. You have to look in the sky a lot to kind of see this. But that's what he was after, was finding that triangulation and understanding the parallax. Maybe tomorrow I will show y'all a quick little sports video about the parallax and kind of how it works. It's easier to understand it with like a touchdown or like a hockey goal than it is for space stuff. Let me stop the video. Thank you for coming to class today. See you tomorrow.